to identify what is possible and to generate data to learn models of the world and sensory motor skills. This is mainly the fundamental difference with continual learning approaches, where the robot does nothing else than start solving a task from the very first moment it is turned on. Many different challenges have to be faced when trying to apply machine learning models on real robots in an open-ended learning setting. Some combine deep hierarchical reinforcement learning and continual learning mechanisms, but the introduced dream architecture is the first one, to the best of our knowledge, that implements most of them, tests relevant approaches, and describes how to connect and articulate them in real robots. The dream architecture additionally considers the building of discrete representations from low-level sensory motor values, building new action representation, state representation learning, passing by symbolic representation, and skill discovery. Starting from a reward that defines a task and policies to observe at least some rewards, the SRL module generates a task-specific state space. This approach relies on raw perceptions. The design of a state space can be seen as chicken and egg problem, as the policy is required to generate observations to be used later, and in order to generate also a new and relevant state space that can be used for learning policies. We tackle this problem here with random policies and a simple button pushing task, but more complex policies could also be generated to bootstrap the generation of state spaces. Although most of the continual learning approaches works are building learning processes that can deal with the continuous flow of data and the different tasks with a single learning process, Dream decomposes the learning into different processes. Some in charge of bootstrapping the representational redescription process, some acquiring skills and consolidating them to make them more robust, etc. Being endowed with a transfer between short-term and long-term memory, the Dream approach includes an instance of dual memory learning system. After the Dream project concluded, we have been recently studying explainable AI as a key dimension of our vehicle towards never-ending learning. But why explainability is pursued? There are different purposes of explainability that are sought by different audience profiles. The reasons to demand explainable models lie in different roles concerned with verifying fair decisions for users, certifying models' compliance with legislation, audits, ensuring new functionality, or simply understanding as domain experts. But what is explainable AI? If we consider the classical definition of Guidotti et al., we thought a relevant dimension was missing in order to properly evaluate explainability. So part of our contribution was putting audience as the key aspect to be considered when explaining a model. So giving an audience an explainable AI is one that produces details or reasons to make its functioning clear or easy to understand. We will use a model as the target of our explainability, considered here to illustrate the different levels of transparency. But we could also have examples, data set, an output class. So simulatability is the ability to simulate strictly by a human. The composability is the ability to explain each input, parameter, or calculation without additional tools. And algorithmic transparency is the ability to understand the process to produce any output where the model has to be fully explorable by mathematical analysis and other mathematical methods. So why is explainable AI actually important for reinforcement learning? With the rapid development of RL, the needs for explanations of RL algorithms and ethical AI systems becomes critical. It's also a requirement for the EU guidelines of ethical and trustworthy AI. And we see some categories refined here from our larger XAI taxonomy, where, for instance, the model can be tweaked to learn simultaneously both policy and explanation. This way, explanations become a learned component of the model, and there are other categories. You can see more in the survey. So on the right, we see an action influence model, for instance, based on a graph that explains a specific action for a star StarCraft 2 agent, we can obtain content factual explanations. For instance, asking the question, why not building a barrack? Indeed, the explanation provided by the graph in bold arrows says, because it's more desirable to do the action build supply depot, since the goal is to have more destroyed units on destroyed buildings. Here is another example of how a trained agent to solve Atari and how it's explained with an explainable AI post hoc method. Saliency maps here can be used to determine what part of an image observation is used by the actor and by the critic. In red, we have the saliency for the critic, in blue for the actor. And the comparison shows the differences among bits, Jacobian saliency and perturbation-based approaches in an actor-critic model. Now, can we use Shapley values, for instance, to explain the contribution of each agent in a cooperative multi-agent RL environment? We have been studying this, and this is the same formula as for the original Shapley value formulation, but instead of feature, we can consider agents, and instead of model prediction, we can use the global reward, so the sum of rewards of all the agents in the considered team. So we have to make M rollouts of the game with different random coalitions to estimate the Shap value of one player with and without you. Now, Explainable AI can provide answers to some of these questions. Can a Shapley value be used to determine how much each agent contributes to the global reward? Or is every agent contributing positively to the common goal? Are they behaving sustainably? What training episodes, key features in observation, or agent actions are actually decisive in the learning? Okay, so another idea we worked on recently is exploiting explainability in order to penalize the model for not mimicking the reasons an expert will use as an explanation of the model. We propose the XAI methodology for explainable neural symbolic learning to fuse deep learning representations with domain expert knowledge graphs. This methodology includes three main ingredients. First, a deep representation learning component, then a symbolic knowledge representation component, here knowledge graphs, and an explainable AI guided learning procedure that we term here Shap backprop training that enforces the alignment of both. With two datasets, we show that the better classification performance, the more explainable the model becomes, and the learned representation allows to remove noisy information. Now, can we add human interventions in the loop that help during learning? The question we pose here, should artificial agents ask for help when in a human and robot collaborative problem solving setting? We take as base an empirical study in a human-robot interaction setting which investigates children problem solving from a developmental perspective. And their main hypothesis is that child-robot interaction problem solving, it's a setting where children that voluntarily interact with the robot are more likely to show better performance and improvements over time than children that interact in a turn-taken setting. Charisi et al. Actually considered this game of Tower of Hanoi and conducted a behavioral experiment to evaluate task performance and designed two types of robot interventions, voluntary and turn-taking. The conclusion of this article that interests us is that the exploration is important in young children problem solving, and that children develop actually inhibitory strategies that emerge and develop in patterns over time. Starting from this conclusion and considering that it would be valuable to transfer developmental discoveries to AI, we try to verify if this hypothesis is also true in a simple reinforcement learning algorithm. We want to check if when solving a simple closed-ended task, receiving help from an expert accelerates the learning of this task depending on whether the intervention is canonical or requested by the agent. In other words, whether the learning is driven by the teacher or by the learner. In this case, we consider the game towards of a node, and our agent learns a simple Q-learning algorithm, and to be as faithful as possible with the behavioral study design, we change two parameters, the canonical intervention rate and the ask for help threshold. Mainly, if the best policy value is lower than the ask for help threshold, the expert will play instead of the learning agent. Here are our results for the two scenarios where we measure success based on the number of moves to resolve the game. Where we see that the learning agent is directly more efficient when it's helped by the expert in a turn-taking scenario. However, it's even more effective when it's helped every 4 turns rather than every 2 turns, showing that it's important for the agent to be able to explore on its own rather than having always the optimal solution. The asking for help agent is also quickly more effective since it does not know yet what to do, but after asking for help many times during the first episode, it starts solving the task by itself, resulting in an increase of inefficient moves. We interpret this as the learning agent gaining confidence in movements which, even if not perfect, it still allows the task to progress towards its resolution through different trials and state explorations. We believe, however, the addition of a mechanism such as intrinsic motivation and the desire for the learning agent to solve the game by itself could increase the accuracy of this comparison. Our learning agent asks for help when it considers that a movement is not good enough to be played, whereas in reality, this mechanism pushing the child to actually ask for help are much more complex. So this is one of the main possibilities for future work to expand on. As future work, we need to explain, we're seeing that recent studies demonstrate that attention is actually not necessarily explanation, and thus we need to be in better position to explain the latest deep learning architectures, reinforcement learning architectures, and the intricacies of this. Also, to better explain the failure modes of explainable AI methods and why and when agents will benefit from human help. Thank you for your attention. Happy to hear your questions.
Thank you, Natalia. Let's see if we have a question. Yeah, Bottom, you can now open your mic and talk.
Hi, very nice presentation, Natalia. I'm really glad that I was able to participate in this conference and hear your presentation.
Hello, everyone. Thank you for inviting me. I am Natalia Díaz-Rodríguez.
Sorry.
Yeah, no worries. So I have like the main question I have is how do you deal with this kind of explainability for very large models? Like, are some models too complicated to explain? And I'm thinking now of like AI models that have millions of parameters, like I don't know, deep convolutional neural networks, for instance. And then the second question would be, if we are talking about explainability, then what is really the trade-off between, explainability of performance?
Yeah, this is a very good question. Let's say it's the holy grail that we are all trying to solve, how to maintain performance and efficiency while not compromising explainability, right? So we see that indeed in our latest work of ex-Mesil neurosymbolic architecture, more, for instance, when we have to detect an architectural style, we take a picture of a facade and we want to say this is Muslim style because it has this Arabic art and this other column of this type. So of course, the more accurate the detector is, the more upgrade with your classifier, but we also see that not always the more performant your overall model, your overall classifier is, it's not always the more explainable. So this is shown to be the case in some cases, in others no. And with real quality of the data, it's very important. Like you really need to make sure that you have signal to pick up and proper annotations that refer to the actual concepts you need to distinguish. So the data quality becomes evident that it's really very important to make sure that it's not unbiased and it's representative of your data, of your problem. And indeed, the more complex your model is, it's harder to track, and there is plenty of work to do still, because as we are seeing, the heat maps sometimes respond to things that we developers want to see. So as long as they seem satisfying for us, we see what we want to see, we are happy with it, but this might not be always the case, or in every case, the explanation we expect. And also this can be hijacked or, suffer counterfactual attacks, for instance, adversarial attacks, sorry. And so it's very important to have counterfactual explanations. That's what I wanted to say. What would have been different to not predict this output, or that is this the same as the expert will agree with, or what we will agree with. So there's plenty of components, and I think the more we account for, the more we are verifying our network, because we need to certify them somehow, and they will be put in production. So definitely a lot of work to do still.
Thank you. And we have one question in Q&A, and probably this will be our last question we're taking before the lunch break. Katarina is asking, I am new to Explainable AI. How are you representing knowledge graph information in deep learning as matrices of ones for each relationships?
Yeah, so in this case, we are simplifying a lot the knowledge graph. We just look at hierarchical relationships, like the object, what we call compositional model. So a whole is composed by the part, a whole object, like let's say a dog has a tail, 4 legs and 2 ears and 1 nose. This is the level that we model in our work so far, but we can also model other things like the family of the animal. Is it, living on earth, in the sea, other things, of course. So far, we have done it very simply, just having a knowledge graph that is not directly ingested by the neural network, but instead, because we know this is a simplification of what the expert agrees, like Romanic art has this kind of arc, this kind of door, this kind of column. So this is rather simple, and it's not needed to feed it. What we do is just that we correct in the traditional gradient descent through backpropagation. We say, okay, if the model, what is the model giving importance to, which attribute, and if this attribute is not aligned with the one that the expert believes is the responsible for that style, then we penalize the model. So it's a bit more like correcting or regularizing the model you could think of in the error, rather than representing and feeding this as a bias. But that's very interesting too, and I think we want to study further graph neural networks and how this would merge the knowledge together from the very beginning. This is always a trade-off of biasing your model or correcting it. And but of course, we think that if there is expert knowledge result from many years, why shouldn't we use it, right? So this is a bit our thinking. So yeah, a lot of exciting approaches to try. Thank you.
Thank you very much, Natalia, and thank you all for attending the morning session. Now we are going to have a lunch break for 1 hour, and we get back here at 1 o'clock. See you all then.
Thank you.
Thank you.